1,000 feet above the world, the war looks almost quiet. The sky over Germany is a hard, metallic blue, thin and bitterly cold. A column of white contrails claws its way across it, a river of ice tracing the path of a bomber stream, hundreds of B-17s and B-24s, wings glittering in the sun, dragging their shadows across the towns and rail yards far below. Their four engines beat a slow, heavy rhythm, each bomber carrying 10 men and a bomb bay full of high explosives toward a country that has already learned to fear this sound. But just ahead of the formation, almost lost in the glare, something smaller moves faster. Sleek shapes weave back and forth, keeping pace with the bombers, climbing above them, dropping back underneath them. North American P-51 Mustangs, their long noses and bubble canopies cutting through the thin air at more than 400 miles an hour. Seen from a distance they look effortless, almost casual, as if escorting heavy bombers to the heart of the Reich at 25 to 30,000 feet is a routine commute. It is not routine for the men inside those bombers. They know what happens when their escorts turn back. They have seen it in 1943, on the deep raids when short-legged fighters ran out of fuel and turned for England while the target still lay an hour ahead. They have watched German fighters swarm the helpless formations, watched entire squadrons vanish in minutes, and read the lost tallies that forced generals to cancel some of the deepest missions because the price was too high. Today, though, the Mustangs are still there, even as the formation crosses the limit where escorts once had to abandon them. Their drop tanks are empty and gone, their engines running hard, but they are still there. Inside each Mustang, bolted just inches in front of the pilot's boots, is the real reason why. It does not look like a secret. It looks like metal and hoses and castings, a V12 engine, 12 cylinders in 2 banks, liquid-cooled, with a supercharger buried deep in its crankcase. Officially, it is called the Packard V-1657. In Britain, its ancestors have a different name, Rolls Royce Merlin. Between those two names lies one of the strangest collaborations of the Second World War, an attempt to take a hand-built British masterpiece and rebuild it in American factories, at American speed, without dulling the edge that made it special. On paper, this should have been impossible. The original Merlin was born in small British shops where skilled machinists hand-fitted parts, polished bearing surfaces by feel, and treated every engine like an individual work of art. Its drawings were in British formats, its fasteners in Whitworth, BSF, BSP, and BA thread forms that did not match any off-the-shelf American tools, its tolerances so tight that a stray human hair could be enough to scrap a component. It relied on craftsmen and measurement systems that Detroit did not use, and did not fully understand. Yet in 1940, with the Battle of Britain barely won and the demand for Merlins far exceeding what British factories could produce, Rolls-Royce and the British government crossed the Atlantic with a proposal. If an American company could take this engine and build it under license, in large numbers, with every bolt and bearing interchangeable with British originals, the Allies could power more Spitfires, more Lancasters, and, eventually, something else, a new generation of high-altitude fighters capable of escorting bombers all the way to their targets and home again. The company that took that gamble sat on East Grand Boulevard in Detroit. The Packard Motorcar Company, famous for smooth, quiet luxury car engines and meticulous craftsmanship. Packard agreed to build the Merlin for both the British and American governments, signing a massive contract in September 1940 and promising to adapt this foreign design to American mass production methods. Less than a year later, the first Packard-built Merlin ran on a Detroit test stand. Between those 2 points in time, engineers had to do more than bolt together parts. They had to translate an entire engineering language. The story you are about to hear begins in that thin, freezing air over Europe, but it will spend very little time there. It will move instead into drawing offices lit by fluorescent lamps, where American draftsmen trace over British blueprints and redraw every single part, thousands upon thousands of them, into a new format without changing a single dimension that matters. It will step onto noisy factory floors where Whitworth-formed taps and gauges are custom ground because no American catalog sells them. It will stand in toolrooms where inspectors compare bolts from Detroit to nuts from Derby and decide whether a bomber crew lives or dies based on whether they turn smoothly. This is the hidden half of the Mustang's legend. The airframe is American. The original idea for the engine is British. The version that actually carried those fighters from England to Berlin and back, day after day, month after month, was something else, a British design, rebuilt molecule by molecule inside an American production culture that believed in long lines, jigs, fixtures, and uniformity. There are no dogfights in this part of the war. There are thread angles, bearing alloys, surface finishes, and a constant fear that in trying to make the Merlin easier to build, someone might blunt its performance just enough to cost a bomber formation its shield. Over the next minutes, this story will walk through 5 turning points. It will step into the bomber formations of 1943, when the United States had bombers and crews and industrial weight, but no fighter that could stay with them all the way to Berlin and back. It will go inside Rolls Royce's pre-war shops to understand what made the Merlin special and why copying it was so hard. It will sit in the Detroit conference rooms where British officials and Packard executives argued not just about contracts, but about philosophy. It will move through the 11 months when Packard engineers recreated thousands of drawings, designed new tooling, and chose to keep British threads instead of replacing them. And it will end here, again, over Germany, in the moment when those choices finally pay off. 3 questions will run underneath everything you see and hear. First, how do you mass-produce a hand-built British engine in less than a year, without softening the sharpness that made it valuable in the first place? Second, how do you keep every part interchangeable across oceans, so that a Packard-built supercharger casing can bolt onto a Rolls-Royce-built crankcase on a field strip in Italy or Burma? Third, when those questions are finally answered, how much does that actually change the air war over Europe? The answers are trapped inside those V-12s, hidden in metal that most people never see. This is the story of how engineers in 2 countries turned that secret into power. And how that power turned the P-51 Mustang from a promising airframe into a war-changing escort fighter. By the middle of 1943, the war in the air over Europe had split in 2. Far below, armies pushed across fields and cities with tanks and infantry. High above them, in air so thin that exposed skin burned from the cold, the United States was trying to wage a different kind of war, a war of daylight precision. Heavy bombers would cross the channel in daylight, find their targets by eye, and break the German war machine, factory by factory. On paper, it was a clean idea. In practice, it was a slow, grinding loss of blood. The bombers went anyway. B-17s and B-24s took off from English airfields in black pre-dawn, heavy with fuel and bombs, and turned east toward a continent wrapped in cloud and flak. They formed up into tight box formations that looked impressive in briefing diagrams and terrifying in the gunsights of enemy fighters. Their commanders knew the numbers, how far to Bremen, to Schweinfurt, to Regensburg, how long it took to reach those targets, and at which invisible line in the sky their escorts would have to turn back and leave them alone. The radius of the fighters defined the limit of what was possible. Early American fighters were brave, fast, and lethal. Inside their own circle, they could protect the bombers to the edge of occupied Europe, sometimes a little beyond. Then fuel gauges and calculations took over. At a certain point, by doctrine and by physics, they had to break away, turn for home, and trust the bombers to survive the rest of the journey. The line where those escorts peeled off was invisible on the map, but bomber crews felt it every time. From that point forward, the formation flew into a shrinking tunnel of time, counting minutes until German fighters appeared. They always appeared. Messerschmitts and Focke-Wulfs attacked in waves, slashing through the bomber boxes with cannon fire, breaking wings, lighting fuel, and tearing men out of the sky. Crews watched whole planes vanish in single explosions. Those who survived saw the pattern. Missions that went deeper into Germany without continuous escort lost too many aircraft, too many men. Loss rates climbed to the point that some deep raids had to be scaled back or paused because there simply were not enough crews and bombers to keep absorbing those blows. The United States had what most nations could only dream of, vast industrial power, thousands of trained aircrew, and an airframe, the P-51 Mustang, that tested well and promised great things. But the airframe was only half of a fighter. With its original engine, it fought best at lower altitudes and could not provide the sustained, high-altitude performance and long legs needed to sit beside bombers all the way to the deepest targets. The shape was right. The heart was wrong for the job. Commanders, engineers, and pilots all understood the gap, even if they spoke about it in different languages. From the cockpit it was simple: when the escorts left, the killing began. From the planning rooms, it was a problem of miles, gallons, and climb rates. From the drawing boards, it was a mismatch between an airframe with enormous potential and an engine that could not hold its breath long enough above 25,000 feet. Somewhere, there had to be a power plant that could unlock what the Mustang's wing and fuselage were already capable of. There was one. Across the Atlantic, Britain had an engine that could breathe at those heights, that could haul fighters and bombers through stratospheric air day after day. The Rolls Royce Merlin had already proven itself in Spitfires and Hurricanes, and its later versions with two-stage superchargers were built to claw for altitude and keep pulling hard where other engines began to fade. The problem was that this engine came from a world of handwork, British gauges, and thread standards that did not speak the same language as American factories. The idea forming in the minds of a few people was simple to state and incredibly hard to execute: put that British engine, or something very close to it, into the American Mustang, and do it in such numbers that entire bomber strategies could be rebuilt around it. The question was how. How do you take an engine born in small British shops and turn it into something that an American company can build by the tens of thousands, at speed, without dulling the edge that made it special? That is where the story leaves the thin air of Germany and steps into the quieter, brighter rooms of a different battlefield. Before understanding what Packard did to the Merlin, it helps to see where the engine came from. In the years before the war, at Rolls Royce facilities in Britain, the Merlin was not just a set of numbers on a drawing. It was a living project, tuned and refined by engineers and craftsmen who knew each other by name. In the machine shops, lathes and mills turned out parts in small batches. Skilled workers checked fits by eye and by touch, feeling for drag, listening to the way parts seated together. It was engineering practiced almost as a craft guild. The Merlin itself was a compact bundle of ambition, a 27-liter, liquid-cooled V12 with cylinders arranged in two banks, designed to produce high power from a relatively slim frontal area. Its supercharger, first single-stage, then in later versions two-stage, was the key to its altitude performance. By compressing the thin air before it entered the cylinders, the Merlin could keep making meaningful power long after a naturally aspirated engine, or a simple supercharged one, had run out of breath. That combination of power, efficiency, and altitude capability turned it into the beating heart of fighters and bombers alike. What made the Merlin hard to copy was not just its geometry, but the way that geometry was achieved. Many early Merlins were, in effect, partially hand-built. Drawings set the targets, but experienced machinists and fitters made judgment calls at the margins. They scraped bearing shells, checked clearances with feeler gauges and intuition, and adjusted parts until each engine ran the way it should. Tolerances were tight, but they were enforced as much by human skill as by automated processes. In that environment, a small inconsistency could be corrected on the bench. In a mass production line, the same inconsistency could scrap hundreds of parts. Even the simplest items told a story about the gap between British and American practice. The Merlin's bolts, nuts, and pipe fittings used British thread systems, Whitworth, BSF, BSP, and BA. Each had its own thread angles, pitches, and profiles, and British factories were equipped to cut and measure them. American industry, by contrast, built its world around UNC, UNF, and related standards. The gauges on the walls and the taps and dies in toolrooms were cut to different assumptions. Try to jam one world into the other without care, and nothing quite fits. The drawings added another layer of separation. British projection and dimensioning standards did not match the conventions used in Detroit. Symbols, views, even the way tolerances were called out could lead to misunderstandings if copied blindly. It was not just a matter of translating words, it was translating the way engineers thought about and communicated the shape of parts. Missing or misreading a small detail on a cylinder block or crankshaft drawing might not show up until an engine was under load at altitude. And yet, through all this complexity ran a simple expectation from the British side: any licensed Merlin built abroad had to be interchangeable with its home-built cousin. A maintenance unit in the field had to be able to unbolt an accessory, a cylinder head, or a supercharger section from a Rolls Royce built engine and install a Packard built replacement without worrying about hidden differences. That meant that whatever changes happened in foreign factories, the functional geometry had to stay true to the original intent. So the challenge for any American partner was not just to build a Merlin. It was to build a Merlin that thought like a British engine but lived inside American industry. Keep the performance. Keep the altitude capability. Keep the tight tolerances. But find a way to do all of that with a different culture of production, different tools, and different expectations. The question hanging in the air was deceptively simple: how do you respect every critical British specification when almost every nut, drawing convention, and measuring system speaks a different language? As Britain strained to keep its own engine factories running under bombing and pressure, the search for outside help grew urgent. The answer, eventually, led to Detroit. Across the ocean, the United States had companies that were already masters of turning metal into machines at enormous scale. Among them, the Packard Motorcar Company had a particular reputation: quiet, powerful engines for luxury cars, built with care and precision. That combination of refinement and volume made Packard a natural candidate when the British government and Rolls-Royce looked for someone to take on the Merlin. Negotiations were not simply a formality. They brought together engineers and managers who had grown up in very different worlds. On one side were British representatives and Rolls-Royce engineers, carrying crates of drawings, sample engines, and long lists of requirements. On the other were Packard executives and designers who knew how to arrange lines of machine tools, how to break an engine into standardized sub-assemblies, how to deliver the same part thousands of times in a row. Between them lay questions of money, time, and, more hidden but just as important, philosophy. For the British, one point outweighed almost everything else: interchangeability. A Merlin built in Detroit had to fit into the same mounts, accept the same accessories, and mate with the same propellers and systems as one built in Derby or Crewe. A spare part produced in Michigan had to bolt cleanly onto an engine in a Spitfire somewhere in North Africa or a Lancaster in Lincolnshire. Any compromise on that front risked chaos in the field, a nightmare of nearly identical parts that could not be safely mixed. For the Americans, the instinct was always to simplify. Converting the engine to American thread standards and fittings would make sourcing easier. Redrawing everything into local conventions and replacing hard-to-manufacture features with more forgiving ones could speed production. All of that made sense if the Merlin were treated as just another engine program. But to do so without care would break the invisible promise that every Merlin, wherever it was built, would be part of one global family. Time pressed on both sides. The agreement between Rolls-Royce and Packard took shape in 1940, backed by a large order. Expectations were clear: in 1941 and 1942, those engines would be needed, not in prototypes, but in service. Bombers and fighters were already flying. Aircrew survival and whole campaign plans depended on engines arriving in real numbers. From the first signatures on those contracts, a clock began ticking over Detroit. When the drawings and sample engines finally arrived at Packard, the company did not treat them as sacred relics. Nor did it rush to strip them of their British quirks. Instead, Packard's leadership handed them to its engineering division with a task that sounded almost contradictory: make this engine truly buildable in American factories, with American methods, while keeping it so true to the original that parts can swap freely between continents. It was not just an order for machines. It was an order to reconcile two engineering cultures under the pressure of war. From that point, the story moves away from conference tables and into the working heart of Packard's plant. There, a different kind of campaign began, one fought with pencils, micrometers, and planning charts, all aimed at turning foreign blueprints into something Detroit could treat as its own without losing the essence of what made the Merlin valuable. The first thing Packard's engineers did, once they had the Merlin drawings in hand, was also the least glamorous: they started to redraw everything. The original details arrived in British projection and notation, loaded with symbols and assumptions that made sense in Derby. In Detroit, those same sheets could hide traps, misread dimensions, misunderstood tolerances, ambiguous views. Rather than risk that, Packard treated the entire engine as if it were a fresh design project. The scale of the task was overwhelming on paper. A complex aircraft engine is not a single drawing but a forest of them: major castings, machined surfaces, small brackets, fasteners, gaskets, gears. Each has its own part number, its own place in the assembly. Packard's drafting rooms filled with these sheets. Teams broke the engine into logical sections and began the slow, careful work of translating every line into American conventions without shifting a critical hole, angle, or surface. This was not copying in the casual sense. Every redraw was an opportunity, and a risk. An opportunity to clarify dimensions, to define tolerances more tightly, to embed the kinds of notes and references that made sense on a mass production line. A risk that, in the process of cleaning up or adjusting a detail, someone might introduce a small divergence from the original Rolls Royce intent. The engineers knew that if they wanted to build thousands of Merlins in Detroit, the drawings had to be beyond question, because machines and workers would follow them without the safety net of hand fitting. At the same time, other parts of Packard were wrestling with how to build the tools that would turn those drawings into metal. Jigs and fixtures had to be designed to hold blocks, heads, and crankcases in exactly the right positions under cutting tools. Gauges had to be created to check critical dimensions quickly and consistently. Entire process sheets had to be drafted, specifying which operations happened first, which came later, and how to catch errors before they multiplied down the line. One of the hardest decisions concerned what to change and what to leave absolutely alone. Packard chose a path that seemed, from a distance, almost paradoxical. They kept British dimensions and thread forms in many places where interchangeability was sacred, even though this meant building or sourcing special Whitworth form taps, dies, and gauges that American shops did not normally use. In other areas, internal features, machining sequences, accessory choices, they allowed themselves to redesign for manufacturability, as long as those changes did not alter how the engine performed or how it connected to the outside world. As the redraw progressed, Packard's engineers had to think not about a single engine but about what happened when the 10,000th one rolled down the line. Hand-built Merlins relied on craftsmen to catch small imperfections as they went. A production line relies on process control. If they loosened tolerances to make mass manufacture easier, they risked engines that ran rough, made less power, or wore out faster. If they tried to hold every exotic tolerance from the British shops without redesigning the methods, production could slow to a crawl. By the time the first American redrawn Merlin drawings were complete, Packard had done more than translate lines. It had embedded the engine into its own way of thinking. The Merlin was still, at its core, a Rolls Royce design. But the path from blueprint to finished part was now written in a language that Detroit's draftsmen, machinists, and inspectors could follow at speed. What remained was the question that hung over every meeting, every fixture, every gauge: even if the drawings and tools were perfect, how do you keep a line of thousands of engines from slowly drifting away from the fine edge that made the original Merlin what it was? Inside Packard's plant, there was one problem that seemed almost trivial from the outside and impossibly stubborn from within: the threads on a bolt. At first glance, a Merlin fastener looked like any other: hex head, steel shank, familiar sheen. Hold a British bolt in one hand and an American one in the other and they seemed interchangeable. But when engineers tried to pair them, the metal told a different story. Angles were off by a few degrees, pitches did not quite match, and what looked like a perfect fit on a workbench could become a time bomb inside a running engine. The heart of it was this: Rolls-Royce had built its world around British thread systems, Whitworth, BSF, BSP, BA. Packard's factories lived in a different universe, one based on American NC and NF standards. Every gauge, every tap, every die, every training manual assumed those American forms. The easiest path would have been to strip the Merlin of its British fasteners and convert every bolt hole, every fitting, every stud to local threads. That change would have been invisible on camera. It would also have shattered the promise of interchangeability with British-built engines. So Packard chose the harder road. Instead of forcing the Merlin into American standards, they decided to bring a slice of British standards into Detroit. Toolrooms began turning out Whitworth form taps and dies that no American catalog supplied in the quantities required. Inspectors learned new thread gauges. Drawings were marked to preserve where British forms had to remain untouched. It was an act of deliberate discipline. Each decision to keep a British thread was a decision to carry extra complexity for the sake of a mechanic on some future airfield who would never know their names. In quiet corners of the plant, another kind of work went on. Precision grinders shaped gauges that could tell an inspector, in a single pass, whether a fastener met the tight limits demanded. Racks filled with bolts stamped and sorted with new care, each batch tracked so that a nut from Derby would spin cleanly onto a stud from Detroit. There were no headlines in this labor, no cinematic moments. Just men and women weighing parts in their hands, checking tiny angles, and refusing to sign off on anything that might bind or strip under load. The payoff came not in applause, but in silence. In the field, mechanics discovered that a Packard-built supercharger housing would bolt to a Rolls-Royce-built crankcase without fuss. Accessories, heads, and other components could swap across oceans and factories. Squadrons did not need to track two separate families of spare parts. They simply had Merlins. The fact that this was rare for a licensed engine program remained, for most people, an invisible achievement. But for the people who had fought the Whitworth problem in Detroit, every engine that ran without incident was proof that the hard path had been worth it. As Packard's production lines lengthened and the first engines began to move from station to station, a quiet decision took shape. The safest way to copy the Merlin was not to relax its standards, but to sharpen them. Where Rolls-Royce had relied on a mix of tight drawings and skilled handwork, Packard sought to push as much precision as possible into machinery, fixtures, and process control. In some areas, that meant tolerances that were not merely preserved, but narrowed. Walk along the line in those months and the shift is visible. Bare crankcases arrive at their first machining stations and lock into fixtures that hold them in fixed relationships under tools set to depths measured in thousandths of an inch. Cylinder blocks move through sequences where surfaces are cut, checked, and recut if they slide even slightly outside defined limits. Surface finishes that a British fitter might once have refined with hand tools are now targeted by machine tools designed from the ground up to hit the right smoothness every time. Packard made changes where materials could be improved without altering the engine's character. Bearing shells, for example, benefited from updated alloys and plating processes that improved run-in behavior and load carrying capacity. Cooling passages were cast and machined to strict standards to support long, hard climbs to altitude. None of these changes asked the Merlin to be something it was not. Instead, they were efforts to give the same design a more consistent foundation, so that an engine built on a Monday afternoon in Detroit would perform like one built on a Friday morning in Derby. Throughout this, one rule remained: the Packard V-1650 had to match the equivalent Rolls-Royce Merlin marks in the metrics that mattered to pilots and planners. Power ratings, boost levels, fuel requirements, altitude performance. These could not drift just because the foundry was in a different time zone. When Packard's engineers did their work well, the results were almost invisible in the cockpit. A pilot advancing the throttle, engaging high gear on the supercharger, or holding maximum continuous power at altitude would feel the same push, see the same numbers on gauges, whether the engine plate carried a British or American name. On paper, the difference between a Merlin 60 series engine and a Packard V-1657 could be captured in a few lines of specification. In reality, The difference was embodied in long rows of machines, in schedules, in inspection routines, and in a mindset that refused to let the pressure for quantity become an excuse for letting quality wander. Those choices, made far from the front, set the stage for what would happen when this American-built version of a British engine met the Mustang's airframe and took to the thin air over Europe. On a test airfield in California, the pieces finally came together. A P-51 stood on the ramp, its long, laminar flow wing promising low drag and high efficiency, its cockpit perched high enough to give its pilot a commanding view. Up to that point, Mustangs had flown behind American Allison engines that performed well at low to medium altitudes but ran out of strength where bombers did their work. The airframe, by contrast, had always hinted that it could be more. The experiment was straightforward in concept. Take this efficient airframe and marry it to a two-stage, two-speed supercharged Merlin built by Packard under license. In practice, it meant more than just hanging a new engine on the nose. Engine mounts, cooling systems, and ducting had to be adapted. Propellers had to be chosen to match the new power curve. Systems that fed fuel, oil, and coolant through the engine and airframe had to work together under conditions far harsher than any ground test cell. When the new configuration flew, the transformation was unmistakable. At bomber altitudes, where the earlier Mustangs had begun to run out of breath, the Packard Merlin P-51 pulled strongly. Its climb improved. Its top speed at 25,000 to 30,000 feet climbed into a range that allowed it not just to keep up with bombers, but to outpace and outclimb many of the fighters sent to intercept them. With drop tanks under its wings, it could now fly far deeper into occupied territory and still retain enough fuel to fight on the way home. Test pilots and engineers measured these gains in numbers, miles per hour at altitude, feet per minute of climb, radius of action with specific fuel loads. Strategists saw them as something else, a tool to redraw the map of what missions were possible. A fighter that could leave English bases, escort bombers to targets deep in Germany, engage enemy fighters over the objective, and then shepherd the damaged home was no longer a dream scribbled in staff papers. It was a real aircraft, powered by an engine whose design had crossed the ocean twice, born in Britain, adapted in America, and now returning to Europe in the nose of an American airframe. By 1944, the Merlin-powered Mustang was no longer an experiment. It had become central to how the United States thought about daylight bombing. Bomber crews who had once watched their escorts turn away at the worst possible moment now looked out and saw P-51 still there, settling into position as the formation approached the flak belts and fighter attacks. Beneath the skin of each of those Mustangs was the same story. British innovation, American production, and thousands of hours spent at drawing boards and machine tools to make a foreign engine feel at home inside a new kind of warplane. Once the Packard Merlin Mustang entered combat in real numbers, the shape of the air war over Europe began to shift. Deep raids that had once meant accepting staggering loss rates slowly became more sustainable. German fighters that had enjoyed near freedom of action once escorts turned back now faced opponents over their own airfields, at their own altitudes, and for far longer stretches of each mission. Escort fighters did not end the danger, but they stretched out a protective screen that bombers could rely on in a way they never had before. Statistics from the period tell a hard story in cold terms. As long-range escorts arrived, loss rates on some of the deepest missions fell compared to the unescorted raids of 1943. German fighter units found themselves taking heavier casualties, both in aircraft and experienced pilots. The Luftwaffe still fought fiercely, but it now had to bleed for every interception over its heartland. The Merlin-powered Mustang was not the only factor in this shift. Radar, tactics, other fighters, and bomber defensive fire all played roles. But it was one of the key enablers that made continuous escort a reality rather than a hope. Behind those operational changes lay the relentless arithmetic of production. Packard's lines in Detroit turned out Merlins in impressive quantities. By the end of the war, American factories had built more than 50,000 licensed Merlins, with Packard responsible for the overwhelming majority of them. Taken together with Rolls-Royce's own output, this meant that an engine that had started as a British project now existed in global numbers large enough to power fighters, bombers, and, eventually, post-war aircraft across several countries. One of the striking outcomes was that Packard's cumulative production of Merlin engines exceeded that of Rolls-Royce itself, even as both companies continued to build variants to evolving specifications. Yet the fundamental interchangeability remained. A field workshop that uncrated a spare engine could install it without concern for whether it had come from a British or American plant. For the crews, what mattered was not the origin stamped on the data plate, but whether it started on a cold morning and pulled properly at altitude. The quiet triumph was that, thanks to the decisions made years earlier about threads, tolerances, and materials, it did. After the war, the story did not end when the guns fell silent. Surplus Packard Merlins found new lives in civilian hands. They powered transport conversions, experimental aircraft, and, eventually, racing machines built to push piston engine performance far beyond wartime limits. At events like the Reno Air Races, highly modified aircraft carrying these engines tore around pylons at speeds their original designers would never have expected. In those moments, the same core architecture that had once escorted bombers over Germany now served a very different purpose, but the lineage was unmistakable. In the end, the story of the Packard Merlin is about more than metal and horsepower. It is about a question that could just as easily apply to any collaboration under pressure: how do you take a masterpiece born in one culture and rebuild it in another without losing what made it great? The answer, in this case, lay in a combination of humility and rigor. Packard's engineers respected the original Rolls-Royce design enough to preserve its critical dimensions and behaviors, and they trusted their own methods enough to reshape the way those dimensions were achieved on the factory floor. There are three strands running through this history. The first is British innovation, born in an island under threat, where the Merlin evolved through trial, error, and courage into an engine that could carry fighters and bombers through the worst days of the war. The second is American manufacturing power, expressed in long production lines, reams of process sheets, and a determination to hit the same tight tolerances thousands of times in a row. The third is the willingness of individuals on both sides to wrestle with small, stubborn problems. Thread standards, bearing alloys, drawing conventions, for no glory beyond knowing that engines would start and run when men needed them. Return, for a moment, to that high blue sky over Germany. The bomber stream is still there. The contrails still stretch from horizon to horizon. The Mustangs still move at the edges and above, restless, ready. It is easy, watching archival footage, to focus on the pilots, the gun crews, the flash of tracers. But behind every one of those aircraft lies a chain of decisions, made years earlier and an ocean away, at drafting tables in Derby and Detroit, at grinders and inspection benches, in meetings where engineers argued over thousandths of an inch and the shape of a thread. If this story has done its job, it makes those invisible decisions a little less distant. The next time you see a P-51 in flight, or hear the high, sustained note of a Merlin running at power, consider the partnership it represents, and the fact that millions of lives, on both sides of the ocean, depended on people who would never set foot in a cockpit. If you want to explore more of these hidden stories, the quiet engineering choices that shaped famous machines, let this be the first chapter. What other wartime legends, in your view, owe their success to work done far from the front lines?